Hi, this is video 2 of 3 for talking about our angular problems. So we're going to look now at something a little different. We're going to review this question for just real quick from what we did from our last one. So I want you to take a look at your cars. Here's your car, the beautiful Corvette, Stingray, and then there's your friend's car. It's a Chevette, not quite so impressive. So here's the question. Tired of playing in the park, you and your friends hop in your car and our cars can go to Culver's. During some part of the trip down Scatterfield Road, your cars are side by side. They have the same speed and the same acceleration. Okay, this is the only time it happens, but this one time. The wheels on your 1965 Corvette Stingray have a larger radius than the wheels on your friend's 1986 Chevette hatchback. Which car's wheels have the greatest angular acceleration? Okay, so which one do you think? Is it your Corvette? Is it the Chevette, or are they the same? Well, let's just take a look. If you need to have more time, just stop the video and think about it. So here we go. The Chevette is the correct answer, and here's why. Okay, basically, you can read the rest of this, but according to the equation of the acceleration is equal to r times alpha, if the linear accelerations are the same and the radius of the Chevette is smaller, the Chevette will have a larger angular acceleration. That does not mean it's a better car, definitely not. And here's some other possible answers that people might have given that would be incorrect. Okay, now I'd mentioned before, we're not going to talk about all these topics with equal amounts or you know, I guess fairness to the topic. This is one of those, okay, rolling motion without slipping. I just want to make sure we just briefly talk about it. The fact that if you've got a bicycle wheel or any kind of wheel that is slipping, that means it's not rolling all the time. It actually, the object can slide without it doing. That would be like on ice, okay? A car on ice, the wheels do not have to be turning and the car can still move, okay? In this case, they're talking about here, you've got two possible situations. In A, the wheel is rolling without slipping. The point P, touching the ground, is instantaneously at rest for just an instant. And then the center moves with velocity v. Okay. Down here in B, the same wheel seen from a reference frame where C is at rest, and now point P is moving with velocity v. The linear speed of the wheel is related to its angular speed. So that's just that little bit about it. The equation that you can't see is V equals R omega. All right. And again, that's all we're going to really talk about with that. Now I want to talk about a major topic, which is torque. Torque is so important in our lives because we deal with it every day with all kinds of things. Right here we talked about a door. Look at the door and you can see that this is something that we have. How many times a day do we go through doors? It's hard. We'd have to count them and it'd be a lot more than what we think. So we've got two things that are happening here. They're saying you could push the door at point B or at point A. Well, I would think that by now, at your age, you know that pushing at point B is not nearly as helpful as pushing at point A. And we're going to see why that is true. There is this axis of rotation, and that's what we're looking at, what we call lever arm. So here's another application of it, any kind of tools where you're actually having something that has to be moved and twisted, like pipes or a lug wrench. Is what that is, where you have the lugs and you're trying to get them to be taken off of the wheel. Okay, now here is a situation where we've got three possible places where you could push the door. We've got A, the force at A, the force of C, and the force of D. I do not know what happened to B. Never have figured that one out on this one. So here's A, B, and C, and you're pushing with the same amount of force. Okay, now if you look there, FD is going to be 0 because if you push that way, there is no movement at all if you push straight on the end. If you push with C, there is some, okay, and we're going to talk about what that does. It doesn't look like it's nearly as productive as pushing with force A, which would be true. So here is what we know about it. If you push with C, the full force goes in this direction at some angle theta, but the problem is the part that's horizontal here, what we would call horizontal, or in the plane with the door, as we mentioned before, there's no motion. So this is really the only part that actually does anything. So we're going to call this a perpendicular force to the object. So Let's look at our first question. It's the one that deals with the door. How much torque is produced on a door if you push on it with a force of 35 pounds perpendicular to the door handle if the door has a width of 2.5 meters? 2.5 meters, 35 pounds. Okay, so we're pushing down this way. There's our torque equation. We plug in our values, and here are the answers. Now, I wanted to do this. I don't do that many problems. We really don't talk much about English, but this one's important because you're going to see this in your everyday life. It's called a foot pound. And even though we think it should be like feet pounds, but it's not. It's a foot pound, and that is the unit for torque. And torque wrenches, that kind of thing, have them. The direction is clockwise. This object is going to move, okay? And so because it's going to move, you have to make sure you have a direction on it. Now, clockwise, we could do positive or negative. That's one of the other options. But then you would just choose positive or negative for each problem. If you do clockwise and counterclockwise, you always have the same direction. It always makes sense. Okay, so in this case, this is clockwise because it's going that direction. All right. Over here, if let's say this was a door that spun all the way around. At this point over here, you'd be going up. So you can't say up or down. That's a relative term that doesn't work. So we would say, because even over here, it's still clockwise. The motion is that direction. And on some of these problems, you'll see what I mean about that. Okay, on this problem, this is a seesaw problem. Seesawing or teeter-totters, of course, have been around for a very long time for kids to play on. And this is one of those things that is fun to think about and interesting. It's got a lot of physics application to it. When I was a kid, I really hated the teeter-totter seesaw with my brothers because they knew I hated getting stuck up in the air. And so they would purposely, because I didn't weigh that much when I was a little kid, they would purposely fix it so that I would be stuck in the air and I would scream and be mad at them. So I did eventually learn to like it, but it's one of those things. All right, so here we go. So we have a clockwise and a counterclockwise. We could put counterclockwise here and clockwise there, it doesn't matter. I usually do it by whichever one I'm solving for. And so the question here is that we have two children, and at the pivot point, so we have the pivot point's in the center, it's fixed. There are two kinds of teeter-totters, one that has a fixed one, and then you have to be able to move. So this would be like just a board. This would be an old-fashioned, the original kind. There are other ones where you can adjust seats, and there's other ones that have like this little thing that looks somewhat like this, and the bar can go through here, and you can actually adjust it and move your teeter-totter so that it will be for better seesawing or teeter-tottering according to the mass of the children, because you usually don't get them that are exact same size. So this one right here, then, if it's in the center, then that is it says it's 4 feet, right? Or 4 meters, excuse me, 4 meters. It's, where it is? I know it's there. My brain it can't see it. It has a pivot in the center. A child with a mass of 6 is 4 meters from the pivot. So this is 4 meters here. And this is 4 meters. Well, excuse me, I said that wrong. We don't know what it is. Sorry. This one's 4 meters. Sorry about that. And this one is a child with a mass of 60 kilograms sits there. And then this one we don't know. Okay, so question mark. So the kiddo this one has to move in or out. And we need to find out, well, if this one's 4, then we know that probably that one is 4 total, right? So it's going to be moving in automatically. It is possible to ask you a question where you would have to figure that out, which we could do. Now on this one then, please note that this was not in English, it was in metric, so we've got kilograms. We have our acceleration due to gravity because remember this is a force, so we would want to have that in there. However, does it really matter? And the answer to that is no, because they would cancel out, okay? So we do the work, and then we see that our R is 3.2 meters, which makes sense because these two have to be equal to have good seesawing. So this guy's gonna have to scooch in, because if he's over here, this guy's only 60 kilograms, this guy's 75, this guy's gonna go down, and that guy's gonna be like I used to be with my brothers and left up in the air. So he's gonna scoot in to get good teeter-tottering. All right. Hopefully that makes sense to you. I think that's a fun aspect of physics. I always like this topic a lot. Okay, now, one more. A lever is 5 meters long, The distance from the fulcrum to the weight is 1 meter. So here we are. This one's 1 meter. And this is a total of 5, and this one's going to be 4 meters. And we've got a worker that's pushing down. Notice that the direction is this way, so this is counterclockwise. If this was, okay, let's say that once we get this rock up in the air, if you were to let go of it, it's going to go that direction. So that is clockwise, okay? So what's the maximum weight that can be lifted? So we're going to have our equation again here. We plug in our values. We've got our clockwise is what we're looking for. And we see that it's 1,600 newtons. All right, that's the end of this video. I wanted to break them up because otherwise it gets too long. We will do it again here in just a minute and finish up everything else.